you all for joining today's Tech Showcase hosted by Business Connect. Our goal today is to celebrate innovative technologies in the wash space and look at how we can continue to improve and grow as a community. And this is important to Business Connect because we work to set up those supply chains to get these innovations to those on the last mile and build it to get to that point. So a little bit of an introduction. Myself, I'm Michelle Bashar, the Chief Marketing Officer of Business Connect, and I will be moderating today's panel along with our three judges. Michael Fisher, he is on his way. Jeremy Lambert, our CEO of Business Connect, and Edgar. I will let you pronounce your last name, I'm sorry. Right. So Jeremy, could you introduce yourself first, and then we'll move on to Edgar.
Yeah, I'm Jeremy Lambert, the CEO of Business Connect, and always excited about this tech showcase. I introduced myself yesterday too, and just love seeing the technologies, the innovations in this space, and how to scale that in a market approach, but with efficacy and the right product for the right place. So yeah, thank you. I love being here.
Hello everyone, my name is Edgar Ngabamana and I work for RTA International. So we are one of the largest non-profit research organizations here in the US, and we are actually headquartered 15 minutes away from here. So I'm an innovation advisor, so I work mostly with S&P 500 companies, but also with some startups to really help them navigate through the innovation lifecycle, so from ideation through market realities.
All right, so this is our scoring rubric. The innovations will be looked at for two different categories. We've got innovation category and the impact category, and then we will have a third award called the Audience Choice Award. So we're excited to offer these three awards that will be presented during the plenary tomorrow morning, so right at the beginning. The Innovation Award recognizes a solution that introduces a new approach with solid technical feasibility supported by evidence. The Impact Award, which recognizes a technology that addresses significant challenge and thought with environmental and societal impacts. And then the Audience Choice Award, which you all get to choose today, and let us know who will receive that tomorrow. The awards will come with hours of consultation provided by RTI and Business Connect. So to follow along and vote and share your rankings for each technology, scan this QR code. You will have a chance to put in your feedback and the number that you are giving to each technology at the end of each presentation during the Q&A time. So it'll be open just for that Q&A portion, and then after on, the mentee will actually change. So it'll be a new input box where you can add that next number for the next presentation. All right, well first I'd like to hand it over to Grace Opeda. She is with Business Connect, sharing the Coldstream FTO Plus. Jeremy will actually be sitting out of this judging because he is part of Business Connect. We want to make sure there's no bias in what is chosen. But Grace, I will pull up.
Thank you, Michelle, so much for the introduction. Like she said, I am with Business Connect as well. I work on the business development side, but today I'm here representing one of our close manufacturers, KLT Filtration. And a quick just aside kind of about KLT. Manufacturing is based in Norfolk, UK, and really neat that all of their manufacturing is powered by renewable energy sources. So they have a wind turbine on site and a solar farm as well. So kind of just a quick kind of background on KLT. And today I'll be talking about specifically the FTO Plus filter, which is a ceramic filter here. And I'll kind of show you guys what it looks like. And you might kind of be like, okay, great, another ceramic filter. We've seen this technology before, but I want to get into why it's special and kind of the specific problems that it addresses. Really that rigorous testing and really pointed contaminant removal. So just going a little bit into that problem that it addresses, I think that there's been a lot of focus on bacteriological concerns, and it is really important that we're preventing cholera outbreaks, and we see a lot of hollow fiber membrane technology being used in filter distributions. but heavy metal contamination is definitely a concern that I think maybe we're not going far enough to address, and we're looking at really just bacteria. And I've listed a few different regions where you see a lot of that. I'll be talking mainly about lead contamination, but this is not an issue even specific to those regions that I've listed. You have mining communities all over the world. You have areas affected by industrial runoff and just rampant industrialization that's really gone beyond what regulation has been able to keep up with, especially in urban areas. So I think we've seen the conversation change a lot, and we're talking a lot more about lead and heavy metal contamination, but more so on that infrastructure side. So US EPA's Get the Lead Out program, which is addressing kind of lead in water infrastructure itself. But I think that it's worth noting that we also have to address the immediate needs of those end users, so looking at it kind of from both sides. And I've linked globalleadfreewater.org just as a fantastic resource. They have a knowledge hub. You can kind of learn more about the scope of the issue and heavy metal contamination. And also, since I'm short on time, there is a QR code up here if you want to scan and kind of read about this systematic review of LMICs, where we saw 632 million children estimated to have blood lead levels over 0.05 ppm. And it's worth noting that there is no safe level of exposure. It's an incredibly potent neurotoxin that affects childhood brain development and impairs cognitive function. And in a lot of these communities, we see a growing disparity because of the effects of that lead contamination. So getting into how this technology actually addresses these concerns, the FTO Plus has been tested for reduction over 150 different unique contaminants. It works with this outer kind of carbon layer and a really robust, this outer ceramic layer and a really robust carbon inner, which allows the adsorption of a lot of chemicals and heavy metals. So we're also still addressing that concern with bacteria, but going a little bit beyond that. And I want to highlight the over 99.35% reduction in lead specifically. And like I said, still addressing those same concerns. And then as far as application scalability, we've seen this filter a lot in high income countries, but there is a place for it in these LMICs. And we've looked at, how can we subsidize the housings or procure them locally? How can you cut down on that initial cost to the end consumer and also set up a supply chain for replacement filters? It's a fantastic fit, also in my opinion, for communities that are a little more adverse to backflushing. And it provides longevity when you set up local supply, and whether that's through subsidization or microfinancing, you have that locally so that people can continue to access clean water. You don't have issues with maybe someone coming in, distributing filters. Okay, what happens when the community next door wants those filters? And that's why I think it's really important that we work with local supply chains. And then just kind of an example of the different kind of applications. You can even be put in a bucket over bucket system and that sort of thing. So, also worth noting that this is the only size that they have of the FTO right now, but KL2 is working on a smaller version to kind of cut down on those initial upfront costs for end users as well as NGOs. That's all. Thank you, guys.
All right, now we'll have 3 minutes of question time. I'd like to start with a question from the audience. Yes? What's the flow rate through the filter?
It's about 4 liters an hour. And you can, I can elaborate a little bit too. You can improve that by multiple filters in like a bucket over bucket system. I think that's per filter. So obviously you see that increase if you have 2 filters in a system or 4. So you can kind of scale that.
So how does the flow rate changes over time depending on the water quality?
Yeah, so great question. The higher the turbidity, you do see a little bit of reduction, but you also have a little bit of power in that regular cleaning and maintenance with just a semi-abrasive sponge or kind of scrubber will keep that flow rate up. It just requires more maintenance. You're just cleaning it a lot more often.
Can you tell us a little bit more about how you clean it up? Is it just, with water, or do you need actually to add
Yeah,
like-
there's just with clean, like purified water, is kind of the best method for it. Like I said, with a semi-adhesive, either sponge or even like a brush for that.
So I have a couple of more questions, but I don't know if the audience has.
Are there any other audience questions?
Since lead is a target contaminant, do you have a version for like schools, something that it's bigger, can be adapted to schools? Yeah, because of the lead.
Yeah, right now, we just have kind of that household scale filter, but as far as scaling it and applying it to schools, I think you can still see that as far as like a housing unit per classroom. But again, it's a little bit more decentralized. There's nothing that's a centralized solution for schools or like a clinic like that. But I guess as big as you can dream with as many filters, your housing can scale up too, theoretically, yeah.
All right, we'll start with Nikki.
Hi. Good presentation, thank you. Is there an end-of-life indicator, or how do you know end of life?
Yeah, there's a blue ceramic inner, so as you clean it and you kind of scrub away those outer layers, once you've reached that kind of change in color, that's your indicator for end of life. So you don't have any like extra parts or pieces that you have to like measure the ceramic by, so there's no like concern of like losing stuff like that. It's just that second layer.
So how do you know the filtration media is actually working? How do you know it's removing lead and all the heavy metals?
I think that there's a place for kind of those like health metric tests. I think that it really is on the side of like water testing. So if you're an organization who's done an implementation and you're doing that follow-up, I think it's just ensuring you have the right testing materials and that either you're leaving that with the community to continually test and maintain those systems, or you yourself are doing that follow-up and just making sure that you're not only testing for bacteria, that you're looking at those other contaminants and you've sourced something that finds that.
I think we have one maybe quick question in the back.
Yeah, what is the estimated production cost, and do you have any sort of initial subsidy plans?
We have looked at working with microfinance institutions, especially in Kenya, but it's a lot of kind of growing that network and kind of figuring that side of it out. As far as cost of production, I want to say institutional prices, so to like NGOs and nonprofits, it's around $25.
I think we are at time, so we will move on to our next presentation. Thank you, Mary. All right, next up is Hank with self-supported supply. And be sure to cast your rating.
I'll still leave this test report up here if anyone wants to look at it.
So I'd like to share a model that we call supported self-supply that, according to our experience, make it possible to reach SDG 6 in sub-Saharan Africa for just $8 billion. So I've been to conferences for 25 years, and for 25 years I hear the eternal headache of maintenance. Of course, it has improved. There's a lot of ideas that have improved the functionality, but it's still a headache. So I have this proposition, and I would like to see hands who would agree with this proposition, which is one way to solve the maintenance problem is to subsidize self-supply, and in general farm wells. So who would agree with this proposition? I can see hands. I see 1.5. Okay, let's go on. So, self-supply means you need to reduce the cost. And the good news is there's a range of new, low-cost, new is not always new, it's improved low-cost technologies that are fit for self-supply. There's wells that cost anything between $100 and $800. There is pumps anything between $50 and $250. There is storage tanks, and there is water filters, because we need to treat the water if you have family wells. Some experiences. So the Yakana organization in Zimbabwe, in Zambia, sorry, had subsidies for 600 wells. These wells, including the pump, cost $1,000, and these wells serve 40 people on average. So that is $25 per person. The interesting part is that 90% of these pumps are functioning. The people around the person with the well have water for free, and the pumps are functioning. Another impact is that there is a creating of the demand for self-supply. So 300 families already paid 100% themselves for a well or a pump. Similar experiences in Tanzania, 700 subsidized wells. Now there is 15,000 row pumps already, and 80% of those are paid for by the families themselves. Nicaragua, 50,000 row pumps used by farmers, and these farmers generate an additional income of $225 a year. So in the last 20 years, the total increased income is over $100 million. And that was done with $2 million of development aid. So, basic service with the conventional approach would cost at least $16 billion, and probably much more. That has to do with the low density of population in most countries. If you would do it with basic service, with self-supply, you can do it for half the cost, because with the combination of wells and water storage, you can do it for $25 per person. Of course, there's concerns. What about the quality? Again, there's a whole stand with solutions. How's the water treatment? The other concern is depletion of groundwater. Again, there is no silver bullet, but there's a range of solutions that you can recharge the rainwater. The logic is all rainwater should go into the ground. One example is deep bed farming in Malawi, where they infiltrate all the rainwater because they make very deep trenches. So the effect of self-supply is the investment cost of $25 per person. The condition is 200 millimeters of rain per year at least. So less headache for the maintenance, but also impact on 5 other SDGs: poverty, food, gender, labor, and climate. So you get 6 SDGs for the price of 1. Bargain. So suggestions are: shift from import to also locally, shift from few wells to more wells for small groups, shift from community to family level, and shift from domestic to productive use. And everything starts with the T. 3 T's to scale up. The first one is training, the second one training, the third one training. Thank you.
All right, we'll open it up to audience questions.
If anybody wants the mic, I've got a mic here too.
Right ahead.
Okay, it's nice presentation and topic. My question is, self-supply could contribute for meeting the SDG targets, but my question is on how the budget flow to self-supply and how countries are committed to implement self-supply. Of course, we know it's cheaper, easily maintainable, but how are things going in terms of budget and countries' commitment?
So the whole logic of self-supply is that you use the willingness of families to co-invest. So it's actually the families are helping the government to reach the SDG 6. If the family is willing to pay half and you subsidize the other half, you reduce your cost that you need from other sources. And you are from Ethiopia, I assume?
Yeah.
Is that true? And Ethiopia is the example. Ethiopia has a new One Wash national program for the next 5 years, and you have included self-supply as a priority to solve the rural water supply system, solve the rural supply for the future. So you are the example of self-supply. Congratulations, by the way.
All right, one more question, then maybe we'll move to the judges for a question.
Yeah, thanks for your presentation. In the section about water quality, you had mentioned like chlorine and boiling and some of these technologies and processes that I think a lot of us are familiar with. But in a lot of contexts, we see problems with uptake and consistency. And it seems like there was a claim here that this system of supported self-supply would improve that. But I'm wondering if you can elaborate more on how we would see different outcomes than we generally see in the literature, which is pretty inconsistent treatment and microbiological outcomes.
Nothing is easy. I mean, first of all, if you promote self-supply, we now say automatically you have to promote household water treatment. And of course you have to invest in awareness, behavior change, so making people understand that clear water is not always safe. So promoting self-supply and promoting household water treatment takes awareness. But it is possible. If you want to know more, tomorrow we have another session that Safe Water for Africa is possible at $4 billion. Tomorrow morning, 8:30, in the Windflower Room. Sorry for the commercial.
All right, a question from the judges?
Yeah, I have a question about the amount to subsidize. So how did you come up with this 50%? And do you think it's sustainable?
So the subsidies, it's based on the experiences that we have in 3 countries, in Zambia, Malawi, and Tanzania. And so the logic again is that if a family is willing, I give you the example from Ethiopia. The government will subsidize up to 50% of the cost of a household well if this well is shared with 5 families. So again, the government or an NGO can subsidize, can stimulate that families invest in their own way if they support and give water to the neighbors. So you would give a subsidy to a farmer who promises that he will share water for domestic use with his neighbors.
Yeah, so what we have seen actually elsewhere is that such a high subsidy will not allow sustainability because it's too high. As soon as we know the well has an issue, then without the subsidy, the family will not be able actually to repair it or to construct another one. So that's why having a higher subsidy is great, to start, to kick off, but then it doesn't allow actually the family to take over time because they only rely on what the government or NGOs are providing.
Well, the logic is that the African Union calculated recently that they need $50 billion to reach SDG 6 in sub-Saharan Africa. So if we want to reach SDG 6, we need to invest, either the government or NGOs or a combination, right? We need all the rural water supply systems are subsidized. The CAPEX, the borehole and the pump. The maintenance is community, but the CAPEX is always subsidized. So why should we not be smart and say, hey, if part of the money is paid by the family, the government needs to subsidize less. So you're using the willingness of families to invest in their own system.
I'll tack onto that question because it spurs another question on for me of, so your proposition is, if it's at $8 billion a year, let's say.
It's a one-time $8 billion.
Well, but, and I think that's part of my question. So I think the sustainability is an important question, piece of this. At some point, that family might not be able to, or dependency on that. The proposition is maybe, the next year it's $4 billion, the next year it's $2 billion, so that family can afford again. Does that fit into the equation for you, or your proposition is one time? So where does the sustainability come in for you in your definition?
It's a one-time subsidy on average. Sometimes it's 20, sometimes it's 40. On average, $5 per person to reach SDG 6. And the sustainability comes from the local production. If you produce road pumps or other pumps locally, you also have the skills to repair them. So we see the uptake of 90%, the functionality of 90% is because they use technology that the people are to repair. But also, since they make money with the pump, they have money to repair it. And that's the sustainability.
All right. Well, thank you. I really appreciate your presentation.
Thank you.
Next, we have Jennifer with Aquasense.
Good afternoon. My name is Jennifer Pagan. I'm the CTO and co-founder of Aquasense Technologies. We are a manufacturer of ultraviolet disinfection systems for water treatment. Our manufacturing is based in Erlanger, Kentucky, which is right over the river from Cincinnati. I am actually based in the R&D office, which is a couple of hours from here in Charlotte, North Carolina. We have global offices, however, in India, Tokyo, Taiwan, Germany, and the UK. So I am not an environmental scientist. I am not a civil engineer. My training is, I'm a PhD in electrical engineering. I am actually, my background, I'm a semiconductor physicist. So I used to work in clean rooms. I did passive micro-optics, and somehow 10 years ago, I co-founded a water treatment company. So I'm going to come on to why that ties into the technology a little bit, but I have a lot of catching up to do with water treatment knowledge and background. But today, Aquasense, we produce a lot of different systems. We're in bottle fillers and ice machines. We operate in a lot of commercial spaces, industrial, pharmaceutical. Have quite a lot of business in pharmaceutical, wastewater, drinking water, at the municipal scale. We even have a system on the International Space Station that's disinfecting the water for the astronauts. So, quite a fun ride over the past 10 years as we've matured this technology. But for those of you who might not know, how does ultraviolet light works? Well, the photons are at an energy such that they can actually damage the DNA of pathogens and inactivate them, so they can no longer cause illnesses by propagating in water or surfaces. However, since the 1940s, all of our UV was generated using what's known as a mercury ballast lamp, or a vapor discharge, gas discharge lamp. They're all various different things, but at the end of the day, they have a small amount of mercury that is enclosed in a quartz tube that contains an inert gas, and it requires kind of a high voltage to create an arc and have the mercury vapor line, which happens to be at 254 nanometers to actually produce the light. Well, when I was doing my postdoc work, I was doing work in various areas of LED, and ultraviolet LEDs were just coming onto the market at that time. So I, being an optics background person, I basically figured out an invention of how to actually harness all of the photons from these LED sources and actually produce a water disinfection system. This is pretty much the first incarnation of the water disinfection system. This is used in a variety of different applications, but just you can see the picture on the right, a 12-watt mercury-based lamp versus a 24-watt LED lamp. I think the size and power density implications are pretty clear. So, you know, today, you know, UVC LEDs are used in a variety of different applications. And we have some, in Colombia, we were used off-grid because these are DC power sources. They just require a few watts of energy, and they're instant on, instant off. So they're only on when the water's flowing. It's a lot of energy savings. We're in drinking water in public schools in Mexico, where they're using rainwater harvesting systems. We're also in industrial and municipal drinking water in various locations. So this is a few of those installations. We've surface drinking water in Norway. We have agricultural reuse water in Spain, and we have a direct potable reuse mobile lab that's going around various places, I think maybe California right now, in the US. So full suite of product ranges from the very small liter per minute up until thousands of gallons per minute. And with that, thank you for your attention. I'll take questions.
All right, starting with the audience.
Thank you so much for the presentation. That was wonderful. I was curious about, you had mentioned rainwater harvesting systems in Mexico. Did you come across like any issues with like turbidity or having to like implement also kind of like a screen for that rainwater harvesting? I'm just curious what what you use in conjunction with it.
Yeah, absolutely. Most UV is used as for drinking water is maybe considered a polishing step. So usually it's used in conjunction with other methods of filtration. So that particular installation in Mexico, they actually did have filtration. I think it was activated carbon for that group that implemented our UV. Yes.
I think on the very last slide and what you were holding up, that was a point of use unit. So is that directly consumable as it's filtering, or do you have to wait for a certain amount of time?
No. So LEDs are on within 9 nanoseconds, so that it's instant on, instant off. So when the water's flowing, the UV's on, and it's instantly disinfecting. So there's no wait time. So these are up to maybe, this size is maybe 4-ish liters per minute. And we have other sizes that are several gallons per minute in this type of form factor.
Thank you.
All right, I think I saw one more over here. Oh, and 2 more.
Thank you for the presentation. Can I ask you where is manufactured and if you import, if you ship to other countries, if it goes through any certification protocol like here in SF, class A and B for UV light? Yeah.
Yeah, absolutely. So we're global, so we have quite a footprint worldwide. We even have a unit in Antarctica on their hydroponic in the Eden. So we are manufactured in Erlanger, Kentucky, so US-based manufacturing. And we have NSF 61, 55, Class B certifications. So yeah, we have, as well as some other international certifications. So you can check out our website. There's some others that are site-specific. There's some in Australia, some in the UK. So.
All right, we've got about 30 seconds, so we can only take one question from the two. Well, go ahead.
Yeah, thank you. Wanted to know, are you operating in sub-Saharan Africa, and then what will be the costs of starting off and then the maintenance costs?
Yeah, so we are an OEM, so we typically partner with NGOs or other manufacturers that are putting together a full system. So we do, we have some various sites, and I apologize for not knowing them off the top of my head. I know in Uganda we have a school and a clinic, but again, we partner versus doing the work ourselves. So people are actually just get our units and install them and combine them with their tech.
Thank you, Jennifer. Yeah, I appreciate it. All right, next we have Turi Tap with Jeremy and Diane.
We're just getting our stand set up over here. Okay. So, hi everyone. I'm Jeremy Lowe. I'm a PhD student at UC Berkeley and also a co-founder of a new nonprofit, Mangrove Water, focused on scaling inline chlorination globally. And I'm joined here with Megan and Amy, also from UC Berkeley and Mangrove Water. And today we're going to be presenting our technology, the TuriTap, and some new updates. So we presented this last year, presenting new updates this year on our progress towards adapting it for use at manual hand pumps. And really this work is motivated by this statement here. And so there was really good research that came out last year from Tim Julian's group, finding that fecal contamination is the primary factor limiting access to safely managed drinking water. And it affects almost half of the population in low and middle income countries. But at the same time, it's estimated that inline chlorination is potentially compatible with over 2 billion people that are currently using these fecally contaminated water supplies. But at the same time, there's around 800 million users of these fecally contaminated water supplies, which are potentially compatible with inline chlorination, including manual hand pumps. So what we mean by this is that there's no real viable or scalable inline chlorination technology for these types of water supply systems at the moment. And so really motivated by this work and motivated by this really dire need and community need, we've been working to adapt the TuriTap for use at manual hand pumps. And so the TuriTap is a passive inline chlorination device, meaning that it doesn't use electricity and it is able to add chlorine into drinking water without requiring or using liquid chlorine at the point of collection. And we originally designed it for use in piped water supply, and so this includes anywhere there's a tap, a storage tank, we can attach it to the outlet of a storage tank, to the inlet of a storage tank, as long as it's compatible with this 6 to 60 liter per minute flow rate. But again, demonstrated by this really dire community need, we have since tried to adapt it for use at manual hand pumps and have been working on this in the last year. And so the main update for you all is that we are currently piloting this in 4 hand pump sites across Kenya and Nigeria. And the short story is that it works, which is really great news. But right now we're in the process of refining the design and trying to make it accessible for users, both from an installation standpoint at manual hand pumps, as well as when people are going to collect the water directly from the point of collection. And right now we anticipate having a hand pump compatible model available in late 2026 based on this work. But the last thing I wanted to mention is that you can buy it now. It's available for purchase through Davis and Shirtliff in East and West Africa. We recently, very, very recently launched sales in September of 2025. So the product page I have listed here on a QR code, but you're also welcome to get in touch with me directly. I have my email posted here, or you can also sign up for updates from us more directly. And I think the last thing I just want to highlight is that, you know, it's been a really large effort, not just from us three, to bring the Terry Tap to market and to do this hand pump adaptation work. So I want to mention, we have our plumber here in Kenya who in the last couple of months has installed over 50 of these in hospital settings there. And also want to recognize partners on this project, CARE Kenya and Remit Kenya, who have helped with prototyping and piloting in these sites. And more recently, Self-Help Africa in Nigeria, as well as funding from GiveWell, Open Philanthropy, and Global Innovation Fund. Thank you.
All right, we'll open up for questions.
How are you controlling the dosing without a pump?
Yeah, so I didn't have a ton of time to go into fluid dynamics, but this is a Venturi doser. So it relies upon the Venturi principle to, as water flows through constriction in the pipe, it's proportionally adding chlorine into the system. So we use that in conjunction with a needle valve. And so this valve is also able to help regulate flow so you can actually set the dose that you want.
We got a question in the back. Jamie?
Thanks for asking too. I always want to explain it, but don't quite have enough time.
Yeah, thanks. This is great to see. I just had questions about manufacturing. Is it in the States and then shipped, or, okay, I'm seeing some nodding. Oh, okay, no, it's not.
Good question.
Yeah.
Yeah, so we're currently manufacturing in Nairobi, a lot of the parts, but then some of the parts are also being manufactured in China and distributed from there.
But it's being assembled and sold in Nairobi through so it's shipping from Nairobi.
Cool, thanks.
Can I ask a question?
There and then we'll.
Okay, sounds good.
Yeah, I just have a question in terms of, in your analysis today, from an addressable market point of view, are you looking primarily at sort of the pre-existing installed base of hand pumps, which obviously over time are going to probably diminish in scale? And I'm just wondering how you factor that into your initial analysis, just in terms of the financial aspects.
Yeah, it's a really good question. I think on our mind, I think like I was mentioning at the start, I think there is this great need still in communities to have a water treatment option at the point of collection at hand pumps, right? Like we're going to still have hand pumps for years to come. I think ultimately the goal is to move more to piped water supply, which the Terry Tap is still compatible with, given the right setting. But I think for the time being, we see there to be great market potential for hand pumps, given that there's no other real viable alternatives.
All right, we've got 1 minute left, so I'll hand it off to Ekta to finish it
Yes,
up.
I have a question about the liquid bleach. This is what you use to refill your system, right?
Mm-hmm.
So how are you going to address any shortage in supplying liquid bleach in those geographic contexts?
Yeah, I think with mangrove water especially, we're thinking a lot about chlorine supply chain and where it's available. I think in our experience, it's been really accessible in some countries like Kenya, but in other places less accessible. I think one thing I didn't mention is that you can use, I think we've seen presentations on this week, and they're out there as well, but the Aqua Research and Stream, you can use on-site generation of chlorine in more remote locations where there are supply chain disruptions to generate chlorine on-site and then use that directly with the Terry Tap. So it's also compatible with that.
Liquid chlorine, there's 3, of course, options. There's electrochlorination, there's diluting bleach, and then there's procurement of WaterGuard, AquaGuard. All of those typically sold liquid chlorine solutions are compatible with the Terry Tap.
Can I steal one more? I love that you've done the next innovation stage of this to get to the hand pump. So is this primarily a mold change? Is this a difference in the Venturi? What is the innovation going to that stage?
Yeah, so what I mentioned briefly is that right now the Venturi does work at hand pumps. for us, it's the design work that we're doing is trying to figure out how to attach it to hand pumps, how to better regulate flow through the venturi in the hand pumps. Because right now it's because it's designed for pipe water, it's a little clunky to do the installation. And so that's like the innovation side that we're trying to do to make it easier for installers and easier for users.
Thank you. Our final presentation for today with IAPMO. The water calculator. Be sure to cast your review for the 2022.
Thanks so much. So my name is Dane Hansen. I'm Executive Vice President of Government Affairs and Global Policy for the IAPMO Group. And many of you who may not be familiar with who we are, I wanted to give you a little bit of background. We are about a 100-year-old federation, a trade association and certification body. So many of the products I would hope that have been talked about today have been certified by us. So in the plumbing and water market throughout the world, we test and certify probably well over 90% of those products. So if you go to your shower tonight, your toilet, your water heater, your faucet, your pipe, you'll see one of our marks. It's a certification mark that either says UPC or IAPMO. So we're the certification body to make sure that they meet the thresholds that they say they do. We work in markets throughout the world to make sure that the product does what they said it's going to do. It's verified, and we work closely with governments to actually implement practices to make sure that products do what they say they're going to do so they don't invest in bad areas. But today I want to talk a little bit about, it's called the Water Demand Calculator. This is a revolutionary system and device. It's actually not a device, it's more of a product that we have developed several years ago to address the oversizing of our plumbing systems throughout the world. So I will just briefly touch on this. So many of you may know, but there was the way that plumbing codes and construction and plumbing systems have been developed over the years was because of a doctor named Roy Hunter from the Bureau of Standards, which was a government agency, the U.S. government back in the 30s and 40s. It's now known as NIST. He developed what's called Hunter's Curve, and this is the algorithm that all plumbing systems have been built on. So how much water is used in a system, what's the geography acclimated changes where systems are not always the same. You know, in Florida is a very different need than in, you know, a desert in Arizona. And so all these climatic changes, the geometry of the systems, this was what he developed. But as you can tell, we are probably much different than we were 100 years ago as a country and in a global economy as well. But the interesting thing with the way our plumbing systems throughout the world have been structured for years is they treat a stadium the same way they would treat a house. And that's true. So if you are building a home, they are using the exact same systems and setup and demand. So it's essentially saying if you turn on every faucet, every fixture, run every toilet, run every shower at the exact same time, that's how you plumb your systems. But how often does that actually work? You know, how often is everything in your system being turned on in your home or wherever it may be? So this is just a forecast. I just put in this briefly to talk about this because you'll see this was done. This is a municipality who tracked their forecast with no conservation methods, but the actual demand went down. So the thing I want to talk about is that I'm going to jump over just because of time. I want to touch on this. Is that right here, you'll see. This is the, I know it's very hard to see, but this is the plumbing products usage based upon the 1940s levels all the way down to current levels. And you can see, you know, back in the 80s, 3.5 gallons flush. It's gone down with EPAC, 1992, and it's gone further, Title 20, 1.2. So you're saying just since the 60s, I mean, since the 80s, we're seeing a 66% reduction, and others in 74% reduction in water use. But yet, we are still plumbing our systems to a much higher level. There's many jurisdictions that have started to adopt the water demand calculator. So you're asking what this is. This is a system, it's an app, it's a program that builders, construction workers, municipalities, anywhere in the world can input how many systems there are, how many toilets, how many showers, how many people are going to be using it, and it will pop out, this is the types of pipes you should be using. This is the diameter of pipes you should be using. Because what we're doing is what you see here is this is a graph that shows the actual demand use. So you can see up the top there, it's just skyrocketing. That's based upon current plumbing specifications and codes throughout the country. But this part down here is just the short breakout from the other one. But as you'll see, that's the current building of our plumbing systems. That is current. But these down here are actually the peak demands for water in the United States today. So you're seeing, look at this is what we're building for. But when you use the water demand calculator, this is what you actually can build for. And the water savings is amazing. So what we're seeing is that systems get smaller. It's safer too. Because if you're oversizing a system, just a very layman example, you have a 3-inch pipe, and if now you're reducing it based upon all water conservation efforts, you now have 80% open pipe. Pathogens grow, everything else develops. So this is a way to save anywhere between $2,000 to $5,000 per home in savings, and a multi-residential could be up to $500,000 in savings. So construction materials go down. So at the end of the day, it's a massive amount of savings, and I'm happy to answer more questions about it.
Over here.
Hello, I'm Katie. I was wondering if the calculator encompasses irrigation, like household irrigation or commercial irrigation with sprinklers.
It does. Yeah, so any sort of water use by the building, any water use, you input this into the calculator, and it will determine, okay, these are the true draws, these are the true demands that will be used in that facility, that building, that apartment complex, that house. And when that is done, it'll tell you, these are the types, these are the piping systems. You should make sure you have 3-inch pipes versus 1-inch pipes. You need to make sure you have your drain pipes smaller because of the incoming water. So it calculates for all that. And we're seeing, like I mentioned, jurisdictions adopting this. Like Charlotte, North Carolina just adopted it for the city of Charlotte, the water demand calculator. So all new buildings have to be built to that specification, which is an enormous water reduction savings for that city. So all new buildings have to meet that, but it is totally attributed to that.
Question from the judges?
So you mentioned, Dane, that this water demand calculator has been adopted in 10 states. This is something that I read. Is it your algorithm, your app? And what's preventing actually other states to adopt it?
Well, there's the political will. There's the political will. There's the unknown. It's a new thing. Plumbing systems have been utilized for, like we said, 100 years, and they've been using an old system. And what we see is there's many countries, and we work globally, so our codes are adopted in Asia, they're adopted in Africa, they're adopted in the Middle East. But what you'll see is that jurisdictions don't know this, and it's only been out for when we launched this 2 years ago. And municipalities and cities work very slow, and so now they're learning about it, and they're saying, hey, we're going to adopt this, and it's a voluntary adoption for now. Then it's going to become a mandatory adoption. So if you want to get a building permit in a jurisdiction, you must abide by the water demand calculator, because it's better on construction costs, it's better on health, it's better on safety. You're just not talking about one house, but you're talking about entire communities that will be fortunately built to a better system moving forward.
Yeah, a follow-up to that, with the states that you're in those zones, areas, there's the longevity of this side of it, the sustainability side, which is, what's today's building and how many people are in that, how much usage is going to be, is not 20 years down the road building that we're going to have, and it's repurposed as a school is repurposed as apartments and things like that. So how does this calculation take those into account?
That's a great question. So part of what we do as an organization is we also do a lot of research and essentially white papers on best practices. So the best thing is that we've even dealt with this in states and counties currently, where certain states have started to convert full office buildings to apartments, but they haven't done it in the best proper way. And so they're doing it, and people are getting sick. There's not as much airflow as needed. There's not as much drainage as needed. So we actually put out guidelines and and white papers on how to convert buildings to new facilities. So if you truly are going to convert something to that wasn't originally built for, we have white papers on how you actually functionally do that safely. And so there is a process in place to run that. And the algorithm it gets smarter and smarter because it's all based upon data. I mean, you're talking millions of data points coming in to tell you how it works. And so this is always going to be evolving, but it's getting better and better every time. And you're seeing states seeing massive savings and saves users money at the end of the day through utility bills, but also through the cost of the building because they're using less materials.
All right, well, thank you so much for your time. All right, we'll just take a minute to put in your rating. It's the same Menti that's been used throughout this session. So feel free to cast your vote for our Audience Choice Awards. That concludes our technology showcase. We will be presenting the awards tomorrow during the plenary, so be sure to be there, especially all the technologies, to see if you are one of the winners. But we really appreciate all the time that you've taken to bring these innovative products to us and continue to encourage you and want to see that growth into the next year. So have a great one, and see you later.
They're kind of tight.
You go out here.
So you haven't used it.
Kind of money problem. Ours are different. Not like you don't have money
The mic.